Hello. Today I'm not going to be talking about epidemiology like I said I would on the sign up spreadsheet. Instead, I'm going to be talking about evolution and a bit of bioinformatics. When I was starting my research on epidemiology, which, by the way, is defined as the branch of medicine which deals with the incidence, distribution, and possible control of diseases and other factors relating to health, I came across a lot of the use of bioinformatics, which is the study of biology with utilization of computers. They used it to quickly analyze data regarding epidemiology and create simulations of disease spreading, and to train neural networks to predict hard to predict biological outcomes. And after seeing all of that, I thought, hey, I know how to code, and I have to do a project on something in biology. So after not thinking about how much time it was going to take, I booted up Unity and started working on an evolution simulator. What I wanted to create was a population of these little tanks from this game called Diep.io, if you've ever heard of it, that would have a little neural network attached to them, and the networks would supposedly evolve due to natural selection when I have them fight each other in an arena. So first I made a little tank that could shoot, move, and rotate, and then I imported some neural network architecture classes that I made a few months ago where I created a handwritten digit recognizer. I created a script that would be attached to the tank that would sense where the two closest enemies were and where the closest wall was in relation to the tank, and then fed those values as inputs to the tank's neural network. The network would then run, and its outputs would be used as the inputs for the controls for our tank, and the neural network will basically act as the tank's brain. So now that I have the tanks, how do I evolve them? Well, basically what I'm going to do is drop as many tanks as I can into an arena, have them fight to the death, and the tanks that kill the most amount of other tanks will get to reproduce. So the next generation will be more like them, basically more likely to kill more tanks, and eventually they'll just all become perfect murderers. You might be wondering about reproduction. How does it work? What genes are they spreading? Well, a neural network such as theirs have these values that dictate how the inputs get turned into the outputs. And these values are just numeric values called weights and biases. All you need to know is that those are the values that control the neural network. If you imagine each weight and bias like a gene, when we perform sexual reproduction on the two tanks, we can just have the child receive either parent 1 or parent 2's gene for that specific value, randomly throughout. Okay, the final piece of the puzzle is mutation. If we're going to train any smart tanks, we're going to need mutation, because mutation will allow us to create new genes, essentially, that we might not start out with. To do this, I just gave any gene of a child a small chance to mutate by a relatively decent amount. Okay, to summarize, we're going to test each tank's fitness by having them fight and giving them a fitness score equal to how many other tanks they kill. Then we're going to take the tanks with the highest fitness scores, use sexual reproduction to mix with the other tanks with the highest fitness scores, and create a new generation of tanks. Each tank in the new generation has a small chance for each of its genes to be mutated, and then we just repeat this process. Oh yeah, and to make it a bit more interesting, I made it so I could add multiple species into the arena, so species could only mate with their own kind. I was hoping that we might see some coevolution or something, so that's why I added it. The process of actually going through and coding all of these different aspects took me a while, since I haven't used a Unity in a few years, and I probably ended up spending more than 8 or 10 hours trying to get it to work. I'll just flash the scripts on screen as a testament of my effort. Okay, so here's the program running. All the tanks are pretty stupid. They're all doing completely random things, and I literally just set each individual's genes to be randomized at the beginning. I left it running for a few hours, with generation times lasting roughly a minute each. I came back and all of the individual tanks were still moving randomly, even within the species. At this point, I kind of expected that the species would have settled around a common pool of genes and would be acting similarly, but I could tell they were not at all. My guess at what was happening was that genes near the bottom of the neural network were having much too high of an impact on how the entire network ran, and that mixing two organisms' genes wasn't creating a cohesive network that could do anything, just a jumbled mix that is kind of useless. It's kind of like how two different species won't usually be able to make viable offspring because they're too different. My hypothesis was that the chromosomal mixing, where we add entire genes, was causing hybrid inviability. The tanks that we were trying to mate with each other were just too different to actually mix and have a child that represented a mix of both traits. Because of this, I decided to create a new system for sexual reproduction, and I decided to take the genes from both of the parents and just average them, and then give it to the child. The idea here is that the species will become similar quickly and will allow for productive mating once they're similar enough as to not cause things like hybrid inviability. I did consider just starting them all at the same spot, so there wasn't as much extreme genetic diversity, but I decided against it because changes to the bottom layers of the neural network can have incredible impacts on the top, and I wanted to keep them fairly stable. I tested my hypothesis and ran 2 different batches using the genetic method for sexual reproduction as well as the average-based mating system. And by finding the average distance of all of the individual's genes compared to the average genes of the population, I graphed the genetic diversity over generations, and we can actually see that on gene-based mating, the genetic diversity went down a little bit, but then seemed to just stay at 6, which is a huge number. While average-based mating, they actually started coming together and acting similarly, which I noticed. As you can see here, all of the blue tanks are rotating and moving in nearly the exact same way, and this was a good sign to me that they were becoming more like a species. What I found kind of weird was that the greens were doing the exact same thing, and it reminds me of convergent evolution. Of course, they could have been spinning the other way probably, but they just happened to be spinning that one way and shooting, and it makes sense that they'd want to shoot and spin. It's pretty much the simplest way to get kills in this environment. Just always be spinning one direction and always be shooting, and you'll probably hit someone, and it doesn't take much effort. My second large modification to the project was simplification. After letting my new model run for about 5 hours, I came back and they were all just spinning. At least I solved the last problem, but they weren't really doing anything cool like aiming at each other. They all seemed to be taking a disregard for their input values and always just shooting and spinning in the same direction no matter what happened. I thought that the large networks were convoluting the process of being able to evolve relatively quickly. Because of this, I was going to simplify my inputs of the tank along with their neural networks to give them enough information and opportunity to develop aiming and strafing skills, but nothing else. As you can see here, it's quite a difference, and it ended up making more impressive feats of evolution possible. Wait, it's actually working. Yes. I'm so glad that happened now. I have to turn this video in like 48 hours. So yeah, the tanks finally learned how to fight properly. At least the blues did. The greens were still spinning and shooting, which only shows how lucky I got with the blues. It seems like some freak mutation in one of the tanks developed, and they developed the ability to actually aim at the enemy tanks. The way I set the program up, the tanks with the most kills get to mate as well as go on to the next generation, which meant a single good tank could skew the entire species gene as long as it survives for multiple generations. I mostly did this in order to counteract the bottleneck effect, where genes can significantly skew over time in small populations, especially when getting kills is so random. I also thought allowing outstanding tanks to affect the species more would be beneficial. When I look back at the footage, from what I can tell, this is the earliest aimer that I was able to find. It must have racked up enough kills to move on, because over the course of the next 10 generations or so, the entire species was changed. I tried to see if the greens would co-evolve, or eventually discover the art of aiming, but after an extra 5 hours of simulation, almost nothing changed. In the end, I'm pretty satisfied with my result considering everything, and I learned a lot about what can lead to more pure or efficient evolution. Things that I would probably change in the future would be 1. The population size. I was extremely limited in population because when I would try and run more than 100 or so tanks and networks at the same time, my frames would drop and the simulation began taking like 10 or 20 minutes per generation. To get around this, I could implement matrices into my networks, as well as multi-threading and GPU compute throughout my program. Number 2 is changing network architecture. What I did to evolve my network was to just go in and manually make it smaller, but using a technique called NEAT, N-E-A-T, you can actually implement evolving neural networks in order to avoid convolution or oversimplified networks. This type of thing isn't always just used for fun demos, but many scientists will sometimes simulate things like this in order to try and predict outcomes in real life. That's all I have, so thank you for watching, and if you want to know more about neural networks, you can watch my video on the application of calculus in backpropagation to train neural networks, if that sounds interesting to you.